Welcome back to this network science project video series by my colleague Anindo Mondal and me, Akanksha Kut. In this video, we are going to cover an overview of the three most popular correlation metrics used in the analysis of financial systems. When we say about correlation, the first one has to be the Pearson product moment correlation, also commonly known as Pearson correlation, after the mathematician and statistician Carl Pearson. The metric is so famous that when someone says correlation, Pearson correlation is the first one that comes to the minds of most people. Now let's get a little technical. Consider the data series x and y, each taking n values, and where xi and yi correspond to one pair of observation. Then the Pearson correlation between x and y is given by this particular formula seen on the screen, which takes value between -1 and +1. Mathematically speaking, the Pearson correlation measures the strength and direction of linear relationship between two variables. But to give a little more intuitive understanding, we can look at the figure on the right. Imagine that we have multiple such x and y pairs, and we plot each observation pair xi, yi on a 2D plane. Then, if this scatter plot closely resembles a line, as we see in the first, somewhat in the second and the last figures, then we can say that we get a high magnitude or absolute value of the Pearson correlation. And as we deviate from a line to a more random distribution of points, as we can see over here, the magnitude of the correlation decreases. Secondly, if y variable increases with an increase in the x variable, we have a positive value of correlation, whereas if y variable decreases with an increase in the x variable, we have a negative value of correlation. Pearson correlation is no doubt the most popular correlation metric used not only in the financial systems but much beyond that. And there are also several variants of this metric in the literature. Some of the interesting articles which I came across during this project are listed down over here. However, there is one key drawback of Pearson correlation, and that it is capable of encountering or capturing only linear relationships. In this figure over here, we can see that if you have a non-linear relationship between variables, something like an x square or 1 by x, the Pearson correlation value is less than what it would be for a linear relationship. And this mainly happens because if you have two variables which are linearly correlated, then the relative position of the mean and the value of the variance can somewhat be mapped to each other when the two variables are linearly correlated. But once you start introducing nonlinearity, the position of the mean as well as the value of variance changes significantly, and such that some of these multiplication pairs, which initially contributed positive values, now start contributing negative values to the overall equation. And therefore, as you increase the nonlinearity amongst the relationship, the Pearson correlation value decreases. Now, therefore, I think this would be the right point to introduce our second correlation metric, which is the Spearman the rank correlation, because this one overcomes the linearity restriction. The key idea is that you rank the values in your data based on their magnitude. And then you basically calculate the Pearson correlation on this ranked data. Now, as it is essentially a Pearson correlation, this also takes values between -1 to +1. However, the main concept is that the ranking process, in a way, gives some linearity to the nonlinear data, as we are mapping from the nonlinear values to an increasing set of numbers, which is linear. And therefore, Pearson correlation on the rank data gives a higher value than on the data itself. Spearman's rank correlation is more generalized than Pearson correlation in the sense that it captures monotonic relationships, which are a broader category than linear relationships, and is also less sensitive to outliers. But real world relationships can be non monotonic and non linear, which is why we'll be discussing one more metric. Just for a quick side note, A monotonic relationship is where the y axis is either continuously increasing or decreasing as we increase the x values. Now, the final metric that we will be discussing is called mutual information. In my opinion, it is not as strictly statistical as the previous two and has its roots in the information theory as introduced by Claude Shannon. A quick disclaimer that the topic of information theory is vast and I'm not very experienced with this field, although I'm going to try my best to convey my understanding of mutual information. Now, the main motivation to study this metric is summarized in the highlighted part. If two variables are related to each other, then it does not matter how complex or subtle their relationship is. Mutual information will give an exact value for the strength of the association measures in bits. This is a line from the information theory book by James V. Stone. This basically means that there is no restriction on the required nature of relationship between two variables for its strength to be effectively captured by mutual information, which is the biggest advantage of this metric. The mathematical formula for calculating mutual information is given as this one, where h of x is called the entropy or uncertainty in variable x, and h of x comma y is the entropy associated with the joint probability distribution of x and y. But to say intuitively, I like to imagine it as these values are the uncertainties which are encountered while while observing the variables independently. Whereas this is the uncertainty when you are measuring the variables together. So if the two variables are somehow more linked to each other, the amount of uncertainty will be reduced. And hence we can say that there is more information transfer between the two variables. Now, to summarize, we see that the Pearson correlation captures linear relationships, Spearman correlation captures monotonous relationships, whereas mutual information can capture any type of relationship. To be really honest, the last one is not true because there is some dependence on the nature of the data and the biases of the data. But for the sake of for the theoretical understanding, this is what we can safely consider.